Okay, so an m by n matrix is a set of numbers arranged in an array of m rows and n columns. Okay, got n columns, m rows. The dimension of the matrix A is m by n. It's often displayed underneath the matrix or down in the subscript as a reminder. Matrix is square if its number of rows equals its number of columns. So for example, if I have something like this, it has nothing to do with the numbers that are inside it. This one is a square matrix. Okay. This one, of course, is not square. Okay. Not square. A column vector is just a matrix with only one column. For example, 1, 2, 9, this way. That would be a column vector. A row vector is it's just a something like this. It's a matrix with only one row. Okay, whatever. The dimension of this would be 1 by 5. Right, 1 row, 5 columns. This one is this is a 3 by 1. 3 rows, 1 column. Now, the transpose of a matrix A is just obtained by interchanging the rows and columns. So, for example, 2, 5, 1 transpose is if I take if I start with a row vector, it becomes a column vector. 2, 5, 1. Or if I begin with a column vector, 3.2, 17, transpose that, I get a row vector, 3.2, 17. Okay. Of course, if I transpose a square matrix, I get a square matrix again. It will not necessarily be the original matrix, but see what happened there? Just transposing the rows and columns. Of course, the dimension of the transpose matrix is the sort of you just flip the two, right? If the first one had m rows and n columns, then the transpose of it will have n columns. N rows and m columns. Two matrices A and B are equal if they have all the same numbers in them. Okay, and of course if they have the same dimension. And matrices that equal the transposes are called symmetric. So for example, if I have something like this, 4, -2, pi, 1, -6.9, -2, pi, 1, -19. This is symmetric, okay? Because if I take its transpose, I get exactly the same thing. It's just flipping about this this diagonal here. If you get the same thing, then it's equal to its transpose. Here's some rules about adding, subtracting, and multiplying by scalars. So if I have a couple of matrices, A and B, you add them, you perform addition on them by performing addition element by element. Same thing with the subtraction. If I multiply by a matrix by a number, also called a scalar, because it scales, right? It sort of lengthens or contracts somehow each of the column vectors. It's just you just take that constant and multiply by every number in there. So, for example, if A equals 421,639 and B equals -5,1, -6,134, and maybe you have some constant equal to 2. Then, in this case, A plus B is just, let's see, 4 and -5 is -1, 1 and -6 is -5, 3 and 3 is 6, right? You just add element by element. Okay, and A minus B, turns out, subtraction is not commutative for matrices, just as it isn't for real numbers, and it follows from the fact that it's not commutative for real numbers, but get what, 917,505, right? Just subtract element by element. I guess I did that right. 9. 1 minus 6 is 7. Negative 6 is 7. 0. 1. 5. 5. Right. Yeah. What about C times A? In this case, C is 2, so that's going to be 8, 4, 2, 12, 6, 18. Right? You just multiply each one of these numbers in A by whatever the constant C is that you're multiplying by. All right, so how do you multiply matrices? Well, there are a couple of ways. The standard way to multiply them is by, well, let me just do an example. What if I tried multiplying C times A? Okay, well, let me just write them together like this. It'll make it easier to demonstrate. 1, 5, negative 1, 0, 1, 0. Times A, 4, 2, 1, 6, 3, 9. Okay. The way this works is you multiply these against those. I'm taking the dot products of these vectors. If you have seen that before, I'm dotting this row vector with this column vector to get, say, 2 times 4 is 2 times 4 is 8, plus 4 times 2 is 8, is 16. Right? 2 times 4 is 8, plus 4 times 2 is 16. Plus 4 times 2 is 16. So you can follow this procedure up here. To get the next one to the right, it's stay in the first row, multiply, take the dot product against with it against this column. Okay, so it's 2 times 1 is 2, plus 4 times 6 is 24. That's 26, right? If I keep on going, I get 2 times 3 is 6. Plus 9 times 4 is 36, that's 42. And now I'm out of columns, so I have to jump to the next row, jump to the next row, jump to the next row. Okay. Again, I'll dot this row with this column. 6 times 4 is 24, plus 1 times 2 is 26. And I should get 12 and 27, and then 14, 31, 48, negative 3, negative 1, and negative 4. Note that C is a 4 by 2, and A is a 2 by 3. Okay, when you take the product of matrices like this, the dimension of the new matrix is going to be this number by that number. So it's notice that is indeed true. It's 4 rows by 3 columns. Okay. What if I instead tried to find A times C? Okay, that's not going to work. I can tell you right now. I've already tried it. I know it won't work. Why? Because the dimensions don't line up like they need to be. All right? I need to be able to dot this row against this column. I can't do it because there's a mismatch here. I've got 3 elements in this row, 4 elements in that column. I cannot dot these. When you dot 2 vectors, when you take the dot product, or also called scalar product, 2 vectors, you multiply element you take the products of the elements this way, and then you sum the products. Okay, so this doesn't make any sense. A diagonal matrix is just a square matrix whose only non-zero elements are along the diagonal. Whose only non-zero elements are along the diagonal. That doesn't preclude it from having zeros on the main diagonal. Okay, but something like this. So that, and this is the main diagonal, by the way, going down from left to right. Okay, so this is an example of a diagonal matrix. The identity matrix I is a diagonal matrix with only ones along the diagonal. Okay, so this is, and sometimes we denote it, with its dimension there to denote that that's, we're talking about the identity. That's a 3 by 3 matrix, or if we had the 4 by 4, that would be the matrix of it looks like that. Okay. Identity matrices are important because they are the multiplicative identities for matrices. If the multiplication makes sense, then if I multiply, for example, if I pre-multiply the matrix A, which is an m by n, by the proper identity matrix, which it has to be m by m, it's got to be square, and this number must match this number here. Then I get the matrix A back. On the other hand, if I post multiply A by the n by n identity matrix, I will also get A back. Okay, but notice that these two identity matrices have to have different dimensions, because on one hand you're multiplying on the left, and on the other hand you're multiplying on the right, and that's important because the A matrix might not be a square matrix. Okay, remember whenever you multiply matrices, the number of columns of the first matrix has to match the number of rows in the second matrix. Okay, and here the number of columns in this matrix must match the number of rows. So these numbers are the same, these numbers are the same. Okay, scalar matrix is just a diagonal matrix whose main diagonal elements are the same and all off-diagonal elements are 0. And you can express it like, something like this, n by n. Okay, so it's so if I had something like 4 times the 2 by 2 identity, that's just going to be 2, 0, 0, 2, like this. Okay. We'll use the 1, j, and 0 notation to mean these kinds of things, okay? For a column of 1s, we'll just write 1 in bold. For a square matrix full of 1s, we'll use j to express that. And if for some reason we ever want a column of zeros, we'll just use a boldface 0 for that. Just to see what this kind of thing, what happens when you multiply say this little matrix here by this is j 2 by 2, right? What happens when you multiply here? You get this against this is 5, this against this is 11, and then again I get 5 and 11. Okay. Notice then that what you're doing is you're essentially summing across the columns, right? By multiplying by 1 here and then multiplying by 1, you're adding these two numbers to get this one, and then adding these two numbers to get this one, and then again you get the same thing in the bottom. What if you went like this? What if you went 2, 3, 4, 7 times 1, 1, 1, 1? Or, for that matter, what if you did 2, 3, 4, 7 times 1, 1, 1, 1, 1, 1. Okay? I know this is not a J matrix, but it's, I guess maybe you could call it a 2 by 3 J matrix. Sure, why not? Then this would be, let's see, now you're summing across the rows, right? 2 plus 4 is 8. 2 plus 4 is 8. 2 plus 4 is 8. Okay? 3 and 7 is 10. Oops, 2 and 4 is not 8, it's 6. Oh my goodness. Don't tell anybody I did that. The columns of a matrix are linearly dependent if one of them is a linear combination of the others. And so you think of the columns of a matrix as vectors, okay? The columns of a matrix, think of them as vectors, C1, C2, Cn, C for column, okay? So when you have n scalars and they're not all 0 and they can be found so that this linear combination is 0, then these column vectors are linearly dependent. That's because you can think of it in two-dimensional space. Let me come up with a couple of let me come up with a scenario here. If you had C1 is equal to 3, 4, and say C2 is equal to negative 9, negative 12. Well, then the idea here is that C1, no, that's not right. C1 sort of points this way, right? This is 3, 4. Transpose. Right? 1, 2, 3, and then up 4. C2, what if I multiplied C2 by a third? Then I would actually get C1 back, and it would come back this way, and I'd be at 0. So these are not linearly independent. In fact, another way to think about this is that I can achieve this vector with a linear combination of this guy. As another example, what if I had V1 equals 3, 4, V2 equals negative 2, 2, and V3 equals 1, negative 6. Well, I happen to know that if I have more vectors than the dimension of my space, in this case I'm in 2 space, then I'm in trouble. I can no longer have linear independence. But let's see what happens here when I try to put these together, when I add them n by n. And I'm just going to let my scalars be 1, and I'll take V1 to be 3, 4. It goes that way. Okay. It's 1, 2, 3. This is 3. Then 1, 2, 3, 4 up here. Now, if I add to this is V1. If I add to this the vector V2, then I'm going to go, let's see, back 2, right, and then up 2. So it'll be here. So this vector here is a copy of V2. This one here is V2. Okay, but this vector here, if I start at the origin and put my arrowhead there, this vector is V1 plus V2. Now what happens if I, whoops, let me put a minus sign on there. What happens now if I add V3? If I add V3, then I'm going to go over 1, back 6. Okay, so and that'll take me back to the origin. Okay, and so by summing these up, or some linear combination of them, it turns out in this case, if you just multiply each by 1 and sum up, then you in fact get 0. Okay, so these vectors are linearly dependent. They're linearly dependent. What about these matrices here? Here, note that column 2 can be expressed as negative 2 times column 1. And so the rank is 2. Okay, the rank is the highest number of linearly independent columns. What if you have something like this? What if matrix B equals 2, 1, 4, 1, 1, 0, negative 3, negative 2, negative 4? Okay. Notice that in this case, column 3 can be expressed as negative 2 times column 1 plus column 2. Right? So the rank in this case also turns out to be 2. Okay. Now if I have something like this, C equals 1, 0, 0, 2, 1, 0, 4, 1, 6. The rank in this case turns out to be 3. It's got full row rank, or full column rank, you could say. And that is because, well, I challenge you, you cannot find numbers, you cannot find a constant to multiply against this column vector, and then another constant to multiply against this one, and another constant to multiply by this one, so that the sum comes back to 0. Right? These are 3 vectors shooting out 3 space. You sum them up, any linear combination of them, you cannot get back to 0. They don't, the 3 of them together, they don't sit in the same plane, is the idea. They don't sit in the same plane. somehow these three column vectors, they all sit in the same plane in 3 space. Same with these. Okay, so the inverse of a square matrix is denoted by this stuff. Okay, what is that? This is what the meaning of the inverse is. Okay, if I take a matrix A and multiply by its inverse on either side, I should get the identity matrix. Now, it turns out that some matrices are not invertible, and we call those matrices non-invertible or singular. Okay, a square matrix with rank that's less than the number of its columns or rows will be singular. Okay, so it's if it's a 3 by 3 matrix, and if its columns are not all linearly independent, then it will not be invertible.